Hey guys, in this video I'm going to show you how to do the fabric simulation using ABAQUS. So before we do that, let me show you how the simulation looks like. So we got a ball dropping on a fabric, and then the fabric got stretched, then the ball bounced back to the air. Because I have gravity in this simulation, so that's why the ball will drop back down again. So we have two parts. One is the ball and the other part is the fabric. Let's start from the ball. I'm going to create and then rename it as ball. And deformable is going to be a shell, and then I'm going to use the revolution function. Continue. So as you can see that the center line here is going to be our construction line. So everything we have is going to revolve, through this construction line. So let me show you how to do it. I got a circle. Then I need a circle to be in 0.5 radius. Okay, so 0.5. This is what I need. And then I draw a line to cut that circle in half. After that, I have to remove the line I don't need. I don't need this line. I don't need this line. So right now, I only have this half circle in here. So what I'm going to do is I'm going to revolve this circle along this axis and make a circle. Down. So in here, I'm going to ask ABAQUS to do 360 degrees, make one full circle. So now we got a circle shell. Let's look at the cross section. So as you can see, this is the shell of the ball. So we got the first one. Let's do the second one. For the fabric, then I create, and then the name is going to be fabric. And then it's going to be deformable shell. So right now I'm going to use the planar function. So the size is going to be 50. Continue. Then I draw a rectangle. Then I can use the dimension function here. It's going to be 20 by 10. Then I click OK. Done. So there you go. So we got the geometry for the fabric. So the next step is to create a material properties for our model. So we have two materials. One is the fabric, the other one is for the ball. So for the ball, I'm going to use the material property from stainless steel. So in here, material, create, steel, and then for the density, I think the stainless steel is about 8,500 kilogram per cubic meter. And then we'll go to mechanical, elastic, Young's modulus. I think the Young's modulus for the stainless steel is 200 gigapascal. So E to the 9. The Poisson's ratio is 0.3. Then, okay. Then we need to create material properties for our fabric. Again, create. Fabric. Then we'll go to the general, go to the density. For the density, I'm going to use 600, which is much lighter compared to the stainless steel. And then we'll go to the mechanical, elastic. So one thing I want to mention is that in here, all the material we use is isotropic. So all the Young's modulus and all the Poisson's ratio, they are going to be the same regardless the loading direction. So for the Young's modulus, I'm going to use 1 gigapascal, which is 200 times more flexible compared to the stainless steel. So 1 E9. For the Poisson's ratio, so basically here is the demonstration showing how the Poisson's ratio is calculated. So the basic idea is that if you stretch the material on one direction, so the other direction it will shrink. So how much it shrink divided by how much is stretched is going to be your Poisson's ratio. Let's go back to the ABAQUS. So in here, I choose the number as a 0.45, which is very flexible. So this number is very close to the Poisson's ratio on the rubber. Then we hit OK. The next step is to create a section for our geometry. So basically, the section is to tell ABAQUS how to apply your material onto your geometry. So let me show you how to do it. Onto this on a section here, right click, create. The first one is for the ball, so I'm going to name that as ball. Shell, homogeneous, continue. For the shell thickness, I'm going to use 0.05. And then the material is the steel, and then OK. So now we have the ball section created. So let me show you how to apply that onto the ball geometry. We double click it, and then we go to the section assignment. We select the geometry, hit down, and then we choose the ball section. So in here, we have different options. We can put that into the middle surface. Also, we can offset that to the top surface. Also, we can offset that to the bottom surface. So let me show you what that means. So each surface has two sides, the top surface and also the bottom surface. So here is the result if you offset that to the top surface. So the surface is on the top. Also, you can offset that to the bottom surface. So all the material is on the top. In here is put that into the middle. So let's go back to ABAQUS. So to me, I prefer to make sure all the material is inside the ball geometry. So I'm going to use the top surface. Hit OK. So let's verify it. So I'm going to check the cross section. So we can go to the view and then go to the part display options. Then we can render shell thickness. Apply. So boom, everything looks good. So everything is inside my geometry. Now we can create a section for our fabric. So in here, the section, create fabric. For the fabric, we use the shell, and then for the type, we choose the membrane. The reason we use membrane is because membrane does not react on the bending moment. So there's only implant tension only. So just like the fabric. Continue. For the material, it's going to be our fabric. The thickness, I'm going to use 0.1 millimeter. So which is 0.0001 meter. Hit OK. Then we apply the fabric section to the geometry. Then double click it and then select the geometry, down, fabric. So because the fabric is the membrane element. For the membrane element, there's only implant tension only. So because of that, all the reaction is assumed to be along the surface. So that's why you don't need to specify the top surface or the bottom surface. Hit OK. The next thing we need to do is to generate a mesh for our geometry. So let's do it for the ball first. Under the ball here, we double click the mesh. And then after we do that, we are in our mesh module. So we go to mesh and then go to element type, select the geometry. Okay, then we choose explicit because we are going to use the explicit analysis for this model. Then explicit shell. Okay, then we have to define the mesh size. We click this button, and then the size I'm going to use for the ball is 0.2 meter. Apply. Then after I do that, I can assign a mesh the part. This is not a perfect mesh, but I think it's good enough, for our analysis. So I'm going to take it as it is. So right now we need to continue to finish the mesh for our fabric. So again, in here, double click and then go to Mesh, Element Type, select the geometry. Okay, then we choose the Explicit again, Membrane. Okay, then we have to select the size of our mesh. We click this button. The number I'm going to use is 0.5. Okay, then we mesh the part. Alright, so we have the mesh for both of our parts. The next step is to put both parts into our assembly module. So go to Assembly, go to Instance, and then hold the Shift key so we can select both parts. And then we auto offset, then we click OK. So now we have two parts inside our assembly. So the next step is that I'm going to move the ball to the center of this fabric. So I'm going to use the translate function from this reference point to this reference point. Then I hit OK. So I need to move it one more time so the ball can be in the center of this fabric. So let me try again. Select the geometry, then hit down. I'm going to use this as my reference point, first reference point, and here is my second reference point. So now the ball is right in the center of the fabric. Hit down, but still not enough. I need to put a ball 10 meters above this fabric. So let's do it again. I'm going to select the geometry, hit OK. Then the first reference point is 0, 0, 0. So on my second reference point, X and Y, they remain in 0. But for the Z, I'm going to put 10 in there. So that means that only the Z-axis is going to, change by 10 meters. Then I hit Enter. So boom. So now the ball is at the location I want it to be. The next thing we need to do is to create a step for our model. So let's go to the step and then right click, create. The type needs to be dynamic explicit. Hit continue. For the time period, it's going to be 10 seconds. Hit OK. So ABAQUS allow you to change your load condition and also your boundary condition during your analysis. So if that's something you need to do, then you have to create more than one steps so you can manage and also control your different boundary conditions. So in this analysis, everything is simple. We don't change anything. So that's why we only need one step. So after the step, we go to field output request. Here, the default one has all the result we need. So I'm not going to change anything here. So in here, I need to change the interval to be 300. So that means that the ABAQUS will generate 300 data points during my 10 seconds of analysis time, which means I'm going to get the result in 30 frames per second. Then we hit OK. Alright, so we are getting there. So right now we need to create the contact surface between those two parts so those two can interact with each other. So to do that, first we go to the properties here, contact, continue, and then we choose the mechanical, tangential behavior. So I need to apply some friction between those two parts. So that's why in here I choose penalty. The coefficient, I'm going to use 0.2. So after that, we go to the interaction, double click. This contact surface is going to be applied on our step 1. And then we choose the general contact, explicit, continue, all with self. That means that this contact surface is going to apply on every single surface on this model. Then the property, we choose the property number 1. That is the one we just created with the friction coefficient of 0.2. Then OK. Now we can define the boundary condition and also the load condition for our model. So let's start from the load first. I want to create a gravity load on this model. So we double click, and then it's going to be mechanical, and then we choose gravity. So we apply the gravity on step 1 here, and then continue. And for gravity, it's on the z-axis. It's going to be minus 9.81. Okay, instantaneous. Okay, so after that, we have to apply our boundary condition. Double click, and then it's mechanical, symmetry, and then continue. Again, we apply the boundary condition as step number 1. Continue, and then we hold the shift key, and then we can select both edges because I want to apply the constraint on both edges. Then okay, then we choose the pin because I don't want to constrain moment, so it can rotate freely. Then okay. So before we run the analysis, I want to add some initial speed for the ball. So I'm going to let the ball having a moving speed of 5 meters per second going down. In the meantime, it also has the gravity applied to that ball. So to do that, for the initial speed, we go to the predefined field. Then, so in here, we choose our initial step. So this is going to be our initial condition for the ball. So we choose mechanical, velocity, continue. We select the geometry. Okay. Then for the ball, I'm going to have 5 meters per second going downward. So that's why it's minus 5 for V3. Okay, so as you can see that it's going to move in 5 meters per second going down. We got everything we need, so we can begin to create some analysis. So to do that, we go to the jobs, create, and then continue. Then we go to the precision tab. So by default, ABAQUS using the single precision to do the analysis. I'm going to change that to double precision. The reason is because the double precision can handle larger deformation better. So that's why I choose the double precision. But keep in mind that double precision requires more computing power. So if you choose the double precision, it will take longer time for your computer to finish the analysis. Then okay. Then I want to do some data check. Okay. So when you do the data check, so ABAQUS will compile all the data you have in your model to check if there is any errors. So there's no errors and everything is completed. So we are good to go. So we right click here and then we submit the job. Again, we can go back to the monitor window to monitor the whole progress. Monitor. So as you can see that the analysis has been started. So we need to wait a little bit. So now the analysis is completed. So in our field output request, we requested 300 intervals. So that's why we have total 300 data points in this table. From the first data point to the 300 data points, it took my computer 142 seconds to complete the whole analysis. So now we can close this window. Finally, we got everything completed, so we can go ahead and verify our result. To do that, we go to our job and then go to result. And I need to rotate a little bit so we can have a better view. And I'm going to also adjust the windows a little bit so we have a bigger view for our animation. And right now, our animation is going to show our von Mises stress. So I'm going to choose this function so we can show the stress contour and also the deformation altogether. And then we can run the animation. Yeah, I think the result looks pretty cool. But because this fabric is a membrane element, so I want to also verify the in-plane principal stress. So to do that, let me post this. To do that, we choose this function. So right now, in this function, we can verify the in-plane principal stress. So here is the stress direction. So let's do the animation for that. Yeah, so I think that's all for this simulation. So this is very simple one, but I have lots of fun working on it. I hope you like it too. So I wish you guys have a good day. Cheers.